to start by talking about when he was Mr. Trump, back before he was first elected in 2016. Okay, and at the time, he was running against Hillary Clinton, and many people, many pollsters had picked Clinton to win. They said she's going to win. She's going to win. No, our polls say she's going to win, and we saw what happened. Okay, so like here, this is what the Huffington Post, a news magazine in the States, basically said, here's Clinton's chances of winning, here's Trump's. Okay, and then we saw what happened in the actual election. So clearly something messed up. Okay, something went wrong. Because Trump ended up winning. So what we're going to do is we're going to focus on something that the polls got wrong in Wisconsin, one of the states. Okay. So what happened is, when the election actually happened, is 60% had voted for Trump. Okay, but it wasn't, the polls weren't predicting that. Okay, the polls were predicting Clinton was going to win Wisconsin. So what happened, that like his poll numbers were in the 40s percentage wise, but he actually ended up getting 60 when it actually happened. Okay. So in a world where 60% voted for Trump, if we take a random sample of 30 voters, what do you think might happen from what we know about proportions right now? Well, wouldn't we assume, like, since we know, like, we know what actually happened, so we know the parameter or the population proportion, it turned out to be 60%. Well, we would assume that if we did samples, it would center around 60%, right? We'd get some below, we'd get some above, so maybe we get one right at 60%. 18 out of 30 voted for Trump, and that's 60%. Then maybe 16 out of 30 voted for Trump, and that works out to, why did I pick that number? Just now I have to calculate it.
52.
52?
This is yes. 50. 53. 53.
53.3.
Oh, because one of the 30.
And then maybe 21 of 30, I'll take one that I can actually do in my head. So maybe in another sample, 70%. But we would assume that it would sort of group around 60%. Okay. And because it was a random sample, sampling method, being random, was unbiased. Okay. So it's unbiased because the sample proportions who voted for Trump centered around 60%. Which was the actual true proportion. So if our sample estimator reflects our population parameter, then we can say that that measure that we used is unbiased. Okay. And what is the key to obtaining an unbiased estimator? It must be random or a random samples, or a random sample. Okay. So in order to do the calculations we did in the last lesson with the mean, to find the average, to find how they center, it has to be a random sample. Okay? What happened in Wisconsin? Well, you can see here, I mean, I know it's hard to see, but these are the pre-election polls. All the blue ones, those were the ones that favored Clinton. All the red ones favored Trump. So you can see all the polls were saying Clinton's going to win Wisconsin. Clinton's going to win Wisconsin. But Trump ended up with 60%. What was the only explanation that could happen because of that? It turned out to be a non-random sample. Even though they were selecting people at random, okay, and I'll explain this in a second. So right now, theirs would be biased. Their polls would be biased, okay? Because their sample proportions did not center around 60%. So you must ensure the sample was randomly selected. Let's do randomly selected from the target population. If it's not, if the condition, if it was not randomly selected, if it was, say, what's an example of sampling? Do you remember an example of sampling that is not random? What?
Never mind.
Okay.
Bad guess.
We learned about some of them in Unit 4. That was the unit without the math. There were a couple of types of sampling that can be done where it's not random. Convenience sampling, where you stand, so you interview the first few people you see. Can you think of another one?
I have a question. What is cluster sampling?
Okay, just a second. Can you think of another one? Yes, voluntary response. You just kind of send it out there and say whoever wants to respond can respond. Cluster sampling
It's still random, right?
is random sampling, like stratify.
Yeah.
Remember we did cluster and stratify together? And cluster is when you random, like if I said I want to survey people in Winnipeg, I'm going to identify all the main neighborhoods in Winnipeg. I'm going to randomly select 4 of them, and I'm going to sample everybody in those neighborhoods. Okay? So if the condition is not satisfied, obviously the estimator is biased. Okay? And so what happened in Wisconsin, or they think that happened in Wisconsin, that resulted in non-random samples, okay, is voters without college degrees had a low response rate for the polling that was done, and a lot of those broke for Trump, okay? And undecided voters broke for Trump more. That's what they figured that happened, but it's just, you know, and we'll talk more about polling when we talk about confidence intervals in the next unit. But, you know, when you see polls, and this is a very brief lesson, okay, they always contain a margin of error, which means it's not exact. Like if you say 52% of Canadians favor Mark Carney with a margin of error of 3%. That means the percent that favor him could go as high as 55, 52 plus 3, or it could be as low as 52 minus 3, 49. That's why when they say, if you've got one candidate who's got 48 and another candidate who's got 47, but the margin of error is, say, 2%, it's a dead heat. You can't say that the one with 48 is ahead because the margin of error could put that person behind, right? Because they could end up being 2 percentage points less and the other one could be end up being 2 percentage points more. Explain how each of the above represents a violation of the random condition. Okay. Well, I mean, basically, we're talking about under coverage, aren't we? Okay. So this would be an example of under coverage. We're missing a whole group of people. So for example, because of under coverage, then we would, or I would say the pollsters would overestimate the proportion voting for Clinton. Okay. So, and I'm just going to skip to the end here, because this is kind of a summary of the conditions we're going to talk about. Okay. I gave you this with proportions in the last lesson. If it's normal, okay, we can do normal calculations on it. If it's random, okay, this is what I can say if it's random. I can say that if I take the average of all the sample proportions I did, it will be equivalent or very close to equal to the population proportion. Okay? So that's this one. But there's other things I have to use, right? I have to be assured that it's a normal distribution. I have to be able to use this formula to calculate standard deviation because I need mean and standard deviation to do normal calculations. So this first condition, the random condition, allows us to say this. Next. Okay. Something called the 10% condition. So we randomly sample 30 major party voters in Wisconsin. 60% of the population will vote for Trump. Calculate and interpret the standard deviation of the sampling distribution. Right? So this is when we did use this formula. So the standard deviation of the sampling distribution was equal to the square root of the population proportion times 1 minus the population proportion divided by the sample size. We used that in the last lesson. So we are told that the population proportion that voted for Trump was 0.6. So it's 0.6 times 1 minus 6 divided by the sample size of 30, and then I take the square root of that whole thing. And I get approximately 0.09. And what does that tell me? Polls will typically vary 0.09 or 9% from the true proportion that voted for Trump. Okay? So that's pretty spread out. And that's fairly spread out. What allows me to use this formula? Something called the 10% condition. Okay? And the 10% condition says that the sample size that I use must be less than 10% of the population size. Or remember, sample size we refer to as little n, population size we usually refer to as capital N. Or in just mathematical notation, little n must be less than 0.1 times capital N. Okay? And if it is, it allows us to use this formula, which we need to do, which we need in order to do a normal calculation. Why does this work? Why is this necessary? Well, here's an example. Okay. 3 situations. So let's say we're sampling with replacements. Okay, that means they're independent. 3 individuals from a population of 10. What is the probability that they're all Republican? Well, what's the probability that the first one's Republican?
6.
Yeah, or 6 out of 10. We could do 6, sure, but I'm going to use fractions. Okay. Oh, sorry. I have that right? 3 individuals. No. Yes. Overthinking. Okay. Those 3 go back into the pool. What's populated, or what's the chance I get 3 Republicans again? 60%. 6 out of 10. Okay. They all go back in. Probability becomes is still 60%, right? So that gives me about 0.216. How much of the population did I sample? 30%, because I did 3 out of 10, right? And that's independent. What if it's not independent? Which is generally what happens, okay? So I sampled 3 individuals from a population of 10. What's the probability they're all Republican? Well, my first chance, 6 out of 10, okay? What's my second chance? 5 out of 9. Because one of those is Republican, okay? And then 4 out of 8. So when I multiply those probabilities together, I get approximately 0.167, which is very different. Keep in mind how much of the population I sampled in these 2, 30%, 3 out of 10. Okay. What if I do 3 individuals from a population of 640? Okay. What is the probability that they're all Republican? Well, now I'm sampling a much smaller percentage of the population, right? I'm sampling less than 10%. Okay. So
What's the probability that the first one is Republican? Out of 640, 384. Is that right?
Make sure I got that right. I don't know why I'm not feeling good about this one. Yeah, that's 60%.
384 out of 640. Probability of the next one, now that that person is gone, one less person, 383 out of 639. And then the third one, 382 out of 638. And when I multiply those three fractions together, I get approximately 2.15.
Very close to this.
So this was independent. This was not independent.
Okay? This was not independent, but it was so close that it's really independent. Technically, it's not, but its probability is very close to being independent. Okay? Because what happens in real life, when you sample people, you don't put them back into the population and resample. You can't do that. Okay? So this is why if the percentage that we're sampling gets too high, this starts to happen. But if the percentage is below 10%, these will be very close to each other. Independence will be maintained.
So what does situation 3 say? Well, that even though we sampled without replacement, our probability is virtually the same as if it was independent. Remember, when you sample without replacement, that's not independent. But because we made our sample size so low compared to the population size, it was virtually the same as if it was independent.
So what does that mean? Here, the 10% condition
Allows us to use this, allows us to calculate the spread. Okay, so we can see the condition that allows us to use this in our formula, that allows us to use this in our whole formula.
now we need a condition that allows us to say, yeah, it follows a normal distribution. And what do we do here? Something called the large counts condition.
The number of successes and failures must be greater than or equal to 10. Okay, or in other words, the sample size times the population proportion must be greater than or equal to 10. And the sample size times 1 minus the population proportion must be greater than or equal to 10. These are successes. These are failures.
Because this is the probability of success. And if this is the probability of success, then 1 minus p must be the probability of failure.
Okay? And if this condition is met, we get to say that the distribution of sample proportions is approximately normal. And again, just to sort of briefly explain why this happens. Okay. Here's an example where we have a sample size that's quite small, 8, and a population proportion that's quite small, or extreme. Okay. If I were to do n times p, or 8 times 0.05, I get 0.4, right? If I were to do n times 1 minus p, well, that would be 8 times 0.95, which is 7.6. Both of those are under 10. You can see what it's going to look like. Okay, it's going to be way over here on a proportion line, and it's going to be skewed to the right because obviously it can't exist lower than 0. Okay. So the extreme p tells us we're going to be close to the edge of the population of the proportion line. The low sample size tells us there's going to be high spread or variation. And the result of that, it's going to be not normal. And we see that. Same population proportion, but a much bigger sample size. So look at what happens when we do NP. We get 800 times 0.05, which gives us 40. And then n times 1 minus p, or 800 times 0.95. Oh, actually, it should give us 760. Yeah, 760. Because these two have to add up to the samples. Okay. Notice these are greater than 10, even though I'm close to the edge, again, because of the extreme low proportion. Okay. It does follow a normal distribution. It's very thin, but it's still normal. Okay. They can be thin or wide. So again, it's close to the edge. But because of the large, or sorry, that should say large sample size. Large sample size is a low variation. And what's the result? It's normal. Now, a lot of proportions in a lot of situations happen between 40 and 60%. So here's one where it's the proportion is 50% or 0.5. Okay, sample size is fairly small. Okay, so the non-extreme p, which means it would be in the middle of the proportion line. Okay. The low sample size will give us the high variation again. But if we did our calculations, if we did NP, we would get what? 10.5? And if we did n times 1 minus p, we would actually also get 10.5. Both of those are greater than or equal to 10. And we see that it is normal.
So as part of the calculations you're going to have to do now, you're also going to have to establish that conditions have been met. Okay?
And so just as the final one here. Okay, the large count condition allows us to say it's an approximately normal shape.
So just to finish this up, we're only going to meet the conditions here. We're not going to do finish the question. Okay. Actually, you can't do it because you're not given enough information.
So the conditions. In a world where 60% of all the students at your school are Republican, you randomly poll 30 students, find the proportion that are Republican, repeat half. Describe the sampling distribution. Okay. Well, first of all, has the random condition been met? Look at the question. And anywhere does it say
That our sample size is randomly selected.
yes? So random condition is met because it says randomly selected. Okay. 10% condition.
Let's assume, and often I will give you this, let's assume that this is a large high school. Okay, so what, a large high school has about what, 1,000 students, at least, somewhere around there? Okay. So let's assume that this high school has 1,000 students, or our high school has 1,000 students. Have we met the 10% condition? Is our sample size less than 10% of the population?
Yes. 30 is less than 10% of school population. Final condition that we have to meet. Large counts. NP, so our sample size was 30 times our population proportion, which was 0.6. That gives us 18. That's good.
Greater than or equal to 10.
Just gonna put that here. N minus, or N times 1 minus P, does 30 times 1 minus 0.6. Gives us 12.
Good as well.
So what am I allowed to say? I am allowed to say that the average of my sample distribution will be equivalent to the population proportion. I will be allowed to say that the standard deviation of my sampling distribution will be equal to the square root of the population proportion times 1 minus the population proportion divided the sample size. And I will be able to assume it's a normal distribution.
Okay.